Hello everyone, all my dear students. In our previous video lecture, we had seen the D-type flip-flop. Now it's time to learn the next concept, and that concept is the edge triggering of the flip-flop. We had seen the clock arrest flip-flop, we had seen the clock D-type flip-flop, but this one is different than the clock flip-flop, and this is we call as the edge triggering. So the flip-flop which is triggered at the edge, that flip-flop is we call as the edge triggered flip-flop. Okay, so in this video lecture we have to see the D-type edge triggered flip-flop. It may be a positive edge triggered or it may be a negative edge triggered. If you will understand this video lecture, then hit the like button, subscribe the channel and share it with your We have to see the edge triggering of the flip-flop, but the question arises, and that question is, what is this edge triggering? We have the clock arrest flip-flop. We apply this kind of clock to the arrest flip-flop, or we can say the D-type flip-flop. Here the clock is like this. If we consider this clock, then here that flip-flop is we call as the clock flip-flop or the flip-flop triggering. Triggering means the change of the state of the flip-flop. Here this is we call as the level triggering. Means the flip-flop triggering is in between these 2 points, in between either this from this point to this point. This is we call the edge, the level triggering. The level triggering means the triggering the change of the state of the flip-flop when there is a high time period of the clock input or there is a low time period of the clock input. When the clock pulse is equals to 1, the clock pulse is equals to 1, or we can say there is a high time. During this high time, how much long this one is, there is a change in the output of the flip-flop, that is we call a level triggering. This edge triggering is different than the level triggering. In the edge triggering, here the flip-flop state is changed at the rising edge or the falling edge. What is that rising edge? Here when we consider the clock pulse, this is the clock input. Okay, so this clock input is applied, and when the flip-flop changes its output during this edge, during this line, I am going to mark here the red color. During this line, then this is we call as the edge triggering. Or when there is a triggering, there is a change of the state of the flip-flop, when there is a falling edge, when there is a trailing edge, then it is we call as the negative edge triggering of the flip-flop. Means when the flip-flop changes its state, when a particular instant occurs, that instant is the rising edge or this leading edge, then it is we call as a positive edge triggering. When the flip-flop changes its state during this time instant, this one time instant, this is we call as the negative edge triggering of the flip-flop. Negative edge triggering and the positive edge triggering. But again there is a question, how we can make the positive edge trigger flip-flop and the negative edge trigger flip-flop, or here the question arises, how we obtain the edge of the clock input, the positive edge and the negative edge. Here we have one circuit, that circuit is we call as the RC circuit or RC differentiator. This RC differentiator is having a input, that input is the clock input, and it is applied to the RC differentiator, and the RC differentiator produces the edge of the clock input. Okay, so here we have to see what is the edge triggering and then why we are using the edge triggering. The edge triggering is nothing but the clock pulse is triggered at either the rising edge or at the falling edge, or you can say at the leading edge or at the trailing edge, or you can say in simple words at the positive edge or the negative edge. So when the clock pulse increasing towards the positive value or you can say when the clock pulse changing from 0 to 1 or low to high, this edge is we call as the positive edge, and when the clock pulse falling from the high to the low value, this is we call as the negative edge of the clock. So when the triggering is done at the positive edge or the negative edge, then that is we call as the edge triggered flip-flop. The flip-flop which changes its state from set to reset or reset to set condition. It changes means it triggers its state from set to reset or reset to the set condition at a particular instant at a particular age, then it is we call as a age triggered flip-flop. If it changes its state when there is a positive edge, then it is we call as a positive edge trigger flip-flop, and the flip-flop which changes its state when there is a negative edge, then it is we call as the negative edge trigger flip-flop. But why we require the edge triggering of the flip-flop? That is the biggest question, and the answer is very simple. If we see the structure of the flip-flop, the circuit diagram of the flip-flop, in that the outputs are applied back to the input. Outputs are applied back to the input. This is we call a feedback. So when the feedback is connected and there is a high time period of the clock pulse, the output may be uncertain. So therefore here we have to change the state of the flip-flop when there is either positive edge or there is a negative edge. Okay, so here there is a question in examination: what is the edge triggering? Why the edge triggering is necessary in flip-flop? So we know what is the edge triggering. The flip-flop when trigger at the falling edge or at the leading edge or at the trailing edge, or we can say when there is a positive edge of the clock or negative edge of the clock, that flip-flop is we call as the edge triggered flip-flop, and this is we call as the edge triggering. The reason of using the edge triggering is to trigger the clock at a particular instant, and that instant may be a change in the clock from 0 to 1, which is we call a positive edge or the negative edge. Okay, the inputs of the flip-flop may change during the presence of the clock pulse due to the internal feedback. Therefore the output may be uncertain, and here for that purpose we use the edge triggering of the flip-flop. Okay, so we seen what is the edge triggering and why we are using the edge triggering. In simple words we can say, when we have to trigger the flip-flop, when we have to change the state of the flip-flop from either set to the reset condition or from reset to the set condition at a particular instant, then we use the edge triggering of the flip-flop. Here the two particular instant we consider. One is when the clock pulse changing from 0 to 1. This is we call as a positive edge. When the flip-flop is triggered during this positive edge during that particular instant, then it is we call as the positive edge trigger flip-flop. When the flip-flop changes its state when there is a negative edge means when the clock pulse changing from 1 to 0 means high to low, this particular instant is we call as the negative edge. It is we also called as trailing edge, or it is we also called as a falling edge. So we got the two types of the flip-flop. Either it may be a positive edge triggered or it may be a negative edge triggered flip-flop. Okay, so we have to see here the circuit again. That circuit is the RC circuit, the circuit which we use for the producing the clock pulse, to convert the clock pulse into the edges. Here the capacitor we use and the resistor we use. This particular combination of the capacitor and resistor is we call as RC differentiator. This kind of circuit is also available. The second circuit is also available, that is we call RC integrator. Means the two circuits are there, RC integrator and RC differentiator. Here the circuit we are using, that circuit is we called as the RC differentiator, and it is in this RC differentiator the capacitor is connected in series with the resistor. Here across the resistor we get the output, and that output is like the edges. Here when the clock pulse is applied, the capacitor is charged exponentially, but the RC charging time constant, the RC time constant is very small than this clock pulse. So here when there is a clock pulse, as soon as the clock pulse is start, here the capacitor gets charged, and as soon as the negative edge of the clock pulse comes here, the capacitor discharges. Means this type of waveform we get. Here this is the waveform we get after the RC differentiator circuit. So just we have to keep in mind, to produce the edges of the clock pulse, here we are using the circuit. That circuit is the RC differentiator. We do not need to know the complete functioning, complete working of the RC differentiator. Just we have to keep one thing in mind. When we apply the clock pulse, when we apply the clock pulse to the RC differentiator, it produces the positive edge and the negative edge due to charging and discharging of the capacitor. But one important thing is there, the time constant, the RC time constant must be very small than the clock pulse time. So we move towards the D-type flip-flop with the edge triggering. We had seen before the clock pulse clock flip-flop. Here we have to see the edge triggered flip-flop, and first we draw its symbol. So symbol is like the clock RS flip-flop symbol, clock D-type flip-flop symbol. Here the D-type flip-flop means here there is a single input, and that single input is the D input. Here it is the D input. The two outputs are there. Which are those? The Q output and the Q bar output. These two are the outputs. Now when we apply the clock input, here we show only the line, and here we mark the input. That input is the clock input. But in this case here, instead of single line, we apply one triangle here, and that is indicating there is a edge triggering. If there is a bubble, then it indicates negative edge triggering. If there is a direct clock input applied to the edge, then it is called as the positive edge triggering. So this is the positive edge triggering. If we have to use the negative edge, then here we apply one bubble. This bubble indicates there is a negative edge. Okay. For positive edge triggering, we connect the clock input directly to this edge. We show here this triangle, means one edge is there, and if there is a bubble, means this is the negative edge triggered flip-flop. Okay. Now we have to see the construction of the positive edge triggered D-type flip-flop. This is the positive edge triggered D-type flip-flop. Why positive edge triggered? Because here this flip-flop triggers, this flip-flop changes its state. Either it may be from set to reset condition or from reset to the set condition. Here this is the positive edge triggered because it changes its state to the opposite state or any other state when there is a positive edge, and this is the D-type flip-flop. So we call it as a positive edge triggered D-type flip-flop, positive edge triggered D-type flip-flop. Okay. Now we apply the input and see what output we get and when we get the output. Okay. Now here the flip-flop we are using, that flip-flop is simply the SR flip-flop or the RS flip-flop. The main flip-flop we are using, and we connect some external circuitry to convert the main RS flip-flop into the D-type flip-flop. Then we use one additional circuit, that is RC differentiator, to convert it into the age triggered D type flip-flop. Okay, so here we have the RS flip-flop, or you can say the SR flip-flop. First we see the functioning of the SR flip-flop, and then we see what kind of output we get if we convert it into the age type flip-flop. Suppose this complete circuit is absent and only this one SR flip-flop is present here. Then what type of output we get, that we see first. Okay, so when S is 0, R is 0, the flip-flop goes into the no change condition. When S is 0, R is equals to 1. At that time, the flip-flop goes into the reset condition, producing the output Q is equals to 0 and Q bar is equals to 1. When we apply the input, S is equals to 1 and the R equals to 0. At that time, we get the output Q is equals to 1 and Q bar is equals to 0. This condition is what we call it as a set condition. One more input is there. That input is when S is equals to 1, R is equals to 1. This condition is we call as the invalid condition. But the invalid condition we eliminate in the D type flip-flop, where the inputs we applied, that inputs are the inverted input. So suppose if we consider now, there is only a D type flip-flop. Here this one circuit is absent. The RC differentiator is absent, and that flip-flop is what we call D type flip-flop. And if there is a D type flip-flop, then the invalid condition not occurs and the remaining conditions are the same conditions. Okay, now we apply the clock pulse to this D type flip-flop and we apply the clock pulse at the RC differentiator circuit. So when there is a positive edge of this clock pulse, here this differentiator circuit produces the positive edge, and here this positive edge is applied to both upper AND gate and to the lower AND gate, and the D input is applied. So here the flip-flop changes its state according to the D input. If there is a negative edge, when there is a negative edge, here it produces the negative edge, but this flip-flop do not respond to the negative edge. Okay, so we consider the input. That input is equals to the low input. That input is the low input, means here this one portion from this point to this point, this one portion of the input. Here we will tabulate all the input conditions in the truth table. So in truth table there is first the clock input, then there is a D input, and the two outputs are there. From that, here we write down only one output, and that output is what? That output is the Qn plus 1. In our previous video lecture, we had seen the concept of the Qn and the Qn plus 1. Once again, I will recall it. The Qn is the condition of the flip-flop just before the clock goes high, and Qn plus 1 is the condition of the flip-flop just after the clock goes high. Okay, so here the clock input, D input, Qn plus 1, or simply you can write down the Q output, and the condition of the flip-flop, either the flip-flop is in no change condition, or it is in the set condition, or in the reset condition. Okay, now first we consider the clock pulse is 0. The clock pulse is 0. What it means? It means that here there is no positive edge. This one time, here I am going to draw. Here this is the clock input. Okay, here this is we call positive edge, and this one is we call negative edge. During this time, from here to here, there is a clock input which is equals to 0. Okay, so when there is a 0 input, no clock pulse, no positive edge or no negative edge is applied. When there is a 0 input, clock pulse is equals to 0. At that time, here whatever the D input, the clock input is equals to 0, means the S is equals to 0 and R is also equals to 0. So therefore here the output is the Qn, and this condition is we called as the no change condition. Whatever the D input, either D input is 0 or D input is equals to 1, we get here there is a no change condition. Now we say the condition when the D input is equals to 0. What? D is equals to 0. So when D is equals to 0, here one input of this upper AND gate is equals to 0. It means the yes input is equals to 0. Now when the clock pulse input changes from 0 to 1, when the clock pulse input changes from 0 to 1, this RC differentiator circuit produces the positive edge. It produces the rising edge here like this. At that time here, one input of the upper AND gate and one input of the lower AND gate both are 1 1, and here see the D input is equals to 0 means D bar is equals to 1. Both the inputs of the lower AND gate are 1 1, so it produces the output. That output is equals to 1, and the upper AND gate produces the output which is equals to 0. So therefore the input for the flip-flop S is equals to 0 and R is equals to 1. The flip-flop goes into the reset condition. The flip-flop goes into the reset condition and produces the output Q is equals to 0 and Q bar is equals to 1. We write down into table. Here there is a positive edge. This arrow indicates a positive edge. The upward arrow indicates the positive edge, whereas the downward arrow indicates the negative edge. Here the output Qn plus 1 is equals to 0 because here the flip-flop is in the reset condition, and we write down here this is the reset condition. Okay, now we consider when there is a D input equals to 1. The D input is equals to 1 and there is a positive edge of the clock input. Here the positive edge comes. Suppose here the next clock pulse is applied and the next clock pulse changing from 0 to 1. When the next clock pulse changing from 0 to 1, it means here for that particular instant here this 0 to 1, this clock pulse is applied to the RC circuit, and this RC circuit produces the again rising edge here like this edge. At this particular instant here the clock is equals to 1. The clock is equals to 1. It means one input of the upper gate is equals to 1 and one input of the lower gate is equals to 1. D is equals to 1. It means the output of the upper gate is equals to 1 and the output of the lower gate is equals to 0. Why the output of lower AND gate is equals to 0? Because the D input is applied inverted to the lower gate. So therefore here its output is equals to 0. Because D is equals to 1, the invert is equals to 0 means one input of this lower AND gate is equals to 0. So its output R is equals to 0. Now we got the condition R is equals to S is equals to 1 and R is equals to 0. It means here the output Q is equals to 1 and Q bar is equals to 0. This condition is what we call, as a set condition. Means when there is a positive edge D is equals to 1, we get the Qn plus 1 is equals to 1. This is we call as a set condition. Now we apply the negative edge. Means what if there is a negative edge? Okay, so here suppose there is a negative edge. Negative edge means what? When the clock input, this one clock input changing from 1 to 0, here the RC differentiator produces the edge and this particular edge is we call as the negative edge. This edge we also call as the falling edge, or this is we also called as a trailing edge of the clock. Okay, so the negative edge means here the clock pulse is applied to the RC differentiator circuit. This RC differentiator produces this negative edge, and during this negative edge here the upper AND gate and the lower AND gate got the input. That input is equals to 0. Here input is equals to 0. D is equals to suppose 1. D is suppose equals to 1. Here output of the upper AND gate and output of the lower AND gate is equals to 0. It means here there is a no change condition. There is a no change condition. Means when there is a negative edge, whatever the D input, suppose D input is equals to 0, again there is a no change condition. Okay, so here D is maybe equals to 0 or it may be equals to 1. We get here the output Qn is equals to what? It is equals to Qn plus 1 is equals to Qn, and this condition is we call as again no change condition. Okay, so once again we write down all these conditions in a truth table in a proper sequence. Okay, so what is that sequence? First we apply the clock pulse having the low input, means there is no positive edge or no negative edge. When there is a negative edge, what is the D input? Either the D input is equals to 0 or D input is equals to 1. We get here the output is the Qn, and this condition is again we call no change condition. When there is a positive edge, means when the clock pulse is changing from 0 to 1, the differentiator produces a positive peak, and here due to this the flip-flop response to the D input, and suppose there is a D input equals to 0, then the Qn plus 1 output is equals to 0, and this condition is we call as the reset condition. When again there is a positive edge and D input is equals to 1, at that time here the flip-flop goes into the set condition and produces the output Qn plus 1 is equals to 1, and here this condition is what we call it as a set condition. There is no invalid condition. Okay, so this is the D type flip-flop. This is the positive edge trigger D type flip-flop. But if you observe this circuit carefully, then you get this circuit's internal circuitry is nothing but the NOR gate flip-flop. See here, this flip-flop we are using, and the two AND gates we are using. Two AND gates additionally we are using to apply the clock input, and this is the internally NOR gate flip-flop. Okay, so this is the positive edge trigger D type flip-flop. What happens if there is a negative edge trigger D type flip-flop, and how we can construct it? Just one change we have to do here, and that change is we have to apply the NOT gate here. We have to apply the inverter here, or we can apply the inverter before the clock pulse, before application of the clock pulse, where we can apply the NOT gate here. At this particular point we can apply the NOT gate, then it becomes the negative edge trigger flip-flop. Either we can apply after producing the edge, or we can apply before producing the edge. Before producing the edge is very easy for the application of the NOT gate. But the important is what is the change in the circuit. What is the change in that circuit? The change in circuit is very simple. Here, instead of the positive edge, this flip-flop responds to the negative edge. Means when there is a negative edge and D is equals to 0, the flip-flop goes into the reset condition. When there is a negative edge and D is equals to 1, then that flip-flop goes into this set condition. Okay, so this is the edge triggered D type flip-flop. It may be a positive edge triggered or it may be a negative edge triggered. So if you understood this video lecture, then hit the like button, subscribe the channel and share it with your friends. Thanks for watching the video. Take care.